Hi, Chris Good here, and we're going to do a video solution to the 8410 Sample Exam 2. So we'll start with question number 1. Use the data in essay marks to make a grouped scatter plot. Okay, so a grouped scatter plot depicting the relationship between the hours spent writing an essay and the percentage grade received, grouped by grade division. So that's in Chart Builder. And we're going to open that up. Just go ahead and click through that, and we're going to just click on scatter plots, and this is grouped plot, grouped scatter right here, and we're going to put essay mark right on the y-axis and hours spent on the x-axis. Right, hours spent writing an essay, percentage grade received is essay mark, and then grade goes into the set color box over there. Click OK, and that should give you a nice grouped scatter plot right here. Were they significantly related or not? Well, let's see. Let's run the appropriate correlation to do that. Are hours and percentage related? It's appropriate to do the bivariate correlation. We'll just drag these two into the variables window, right? And there we go. So we've got 0.077 as the p-value that's associated with our Pearson correlation of 0.267. We would fail to reject the null, so they are not quite related, because that p-value, this one right down here, right, and this is the same one over here, essay mark versus hours spent on essay, 0.07, we fail to reject the null that this relationship is 0, because it is unlikely, but it's not too unlikely that we would get a value of 0.267 if the Pearson correlation value in the population is 0. Alright, next, use the data in T Makes You Brainy 716 and run a simple regression. So go to regression using cups of T as a predictor and cognitive function as the criterion. I'm going to make that my active window. T Makes You Brainy, linear regression, and cognitive function is our criterion. Number of cups is independent. Simple regression, is the relationship significant? So we'll say OK, and we'll run that regression. Here it goes. Here's our model summary right here with the R-square. Here's the ANOVA with the p-value there, and here's the coefficient right here. The question, so the relationship is significant. How do we know that? Because if you look at the ANOVA for the whole model, right, the p-value here is 0.038. That's less than a reasonable alpha of 0.05. And we'll conclude that, yes, this model, the whole model, predicts cognitive function significantly. And here's the coefficients table to answer the rest of the question. What should the value of cognitive function be when one drinks 0 cups per day? Well, when 0 cups per day is drunk, then we'd go to the y-intercept right here, which is 49.218. And that is what the score would be when the predictor value is 0. That's the y-intercept. And what proportion of variance in cognitive function is shared with cups of tea drunk per day? Well, that would be the R-square value right here. So it's 0.6% right there. All right. Just to point this out, that b sub 1 down here, this unstandardized coefficient, this means that this is how many points your cognitive function increases with every cup of tea. So to get another 4.6 points on the scale the researchers used, you'd have to drink 10 cups of tea every day. Alright, last question. Use the data in supermodel.save, there's the supermodel data, to test the regression model with age, the years worked as a model, and attractiveness rating to predict salary. which factors significantly predict salary? Are there any problems with the particular regression model? And what are they? All right, let's do this a couple different ways. First, go to linear regression, and we're trying to predict salary using all three of these things. Okay. If we force this regression, just like that, and look down here, the overall model is significant, right? We get P is very, very tiny. So the model does significantly predict salary. But if you go down here into the coefficients, right, and look at the p-values associated with these first two that were added in there, age and number of years as a model, the p-value is less than a reasonable alpha, which means that this unstandardized coefficient, age, and number of years as a model, which actually varies inversely with salary, these are significantly different from 0. So they have predictive value. But attractiveness down here, even though we have an unstandardized coefficient that's negative, interestingly enough, it's actually not significantly different from 0. With a p-value of 0.199, that's larger than a reasonable alpha. So that's the way that works. If we do it as a different kind of model, so if we did this as stepwise instead, we should end up with the same thing. So if we go to linear regression and choose stepwise, right, then we actually get this, there's only two models that are generated, and attractiveness is left out of this last one because it doesn't add to the predictive power of the overall model. And you'll see that if we did the, I forgot to click on the R-squared change, but if we did that under statistics, we'd see how the model changes when we add in that extra predictor. We start off with a single predictor, and the R-squared change increases a little bit. That second predictor, it just doesn't add that much to the model. We could have taken another look at potential problems with the model, right? So we could have checked the case-wise diagnostics. We could have looked, one thing we could have looked at is the PP plot of the residuals, and we might find that they don't look like they're normally distributed. We might look at the z-pred, z-resid plot, and if we did that, let's go ahead and look at that under the statistics plots. So if we plot z-pred and z-resid, right, and do these standardized residual plots as well, the PP plot, we might detect some problems with that model, right? So the plot of the PP plot of the regression standardized residuals shows that some sagging here away from the diagonal. That suggests that those residuals are not normally distributed. That's one of the assumptions. This is a really good example. All these points lining up on the diagonal over here. Field calls it funneling, but when things are clustered along this line on the z-pred, z-resid plot, that suggests we violated heteroskedasticity. Both of these suggest that our p-values should not be trusted, and if you went ahead and did these extra steps, and I do consider that sort of above and beyond, that might have been worth some extra credit on the exam. The last bit is to do a t-test on the data in goat or dog. So we're going to open this new data file, goat or dog, and do the t-test. And it says, is there a significant difference in life satisfaction depending on whether you married a goat or a dog? Thanks, Andy Field. Alright, so these are two different people, two different categories of people who got married, so they're independent samples. type of animal is the grouping variable, and life satisfaction is the test variable. Remember, we're going to define those groups, and oops, I'm going to back out of this just to check and see how we're coded. It's actually coded as 1 and 2, right? So let's go back to our compare means. Independent samples Ttest. Life satisfaction is test. Type of animal is grouping variable with 1 or 2 as that wife choice. And let's look at the Ttest output. So we've got our means from the two different groups. Unequal ends, that's actually not a problem. In the independent samples Ttest, Levine's test for quality of variance, we've passed that, right? So we don't use the adjusted degrees of freedom. This p-value is above a reasonable alpha, so we assume equal variance. So t is negative 3.446. It means that life satisfaction is greater with the dog than with the goat, because we can look at the means. And the p-value is 0.003. We'll declare this significant, reject the null. And calculate the effect size as follows. So we can take the square root of t squared over t squared plus degrees of freedom to get r, right? And that's a measure of effect size, right? So if we square our t value, 3.446, right, and we add that to our degrees of freedom, which were 18 because we didn't adjust them, right? I'm actually going to copy that value, and I'm going to take the squared t value, 3.446, square that and divide it by the value that we pasted. That gives us r squared. If we take the square root of it, then this gives us r of 0.63, and that is a fairly robust effect size right there. Conduct a linear regression on the same data with using the wife variable as the predictor variable. What's the value for the t-test in that regression? Well, if we do a simple linear regression, life satisfaction is the dependent, type of wife is the independent, right? Okay. For the coefficient, the t-test in the regression has exactly the same value, but it's opposite in sign, right? The p-value is also the same. And that just has to do with how we coded these two variables, right? We'd have to go back to the means to figure out what the t-test and the linear regression would say about the direction of that difference. So we'd still need to look at some descriptive statistics there. And it's the same because it's actually the same test, right? So this t-test is comparing this unstandardized coefficient with a value of 0, and this value should equal the difference between these two means. And let's go ahead and just show that that's actually true. So the difference between these two means is 60.13, and 38.17, which, 60.13 minus 38.17, all right, 21.96, exactly the same thing as the unstandardized b here, because remember, the intercept should be the value of one of the means, and the b sub 1 should be the difference between those two. All right, that's it.